Let's study 9th Standard ICSE Physics, Chapter 3C, Newton's second law of motion, the law of momentum.
Now, this law is the fundamental law out of the three. To understand this law, first we have to understand the concept called momentum. Momentum, P, is nothing but the product of mass into velocity. Now, this is called linear momentum because there is another concept called angular momentum which is not in our syllabus. Now, since velocity is a vector quantity, so momentum is also a vector quantity. Even force is a vector quantity, but not mass, that's scalar. And the SI unit, as you can guess, is kg into meters per second. But what is the need to invent a new quantity called momentum? Imagine that we have two vehicles, let's say a bike and a truck, and both of them are moving with the same velocity, let's say 50 kilometers per hour. And you have acquired superpowers with the help of which you can even stop vehicles with your bare hands. You can pick up any character from Marvel or DC, stop the bike or the truck moving with the same velocity. In which case would you be required to apply a greater force to stop the vehicle? It will be more difficult to stop the truck because it has greater mass. There are two trucks with the same mass but different velocities. Truck 1 is moving at 50 kilometers per hour and truck 2 is moving at 100 kilometers per hour. Now, which one is easier to be stopped? The one with a lesser velocity will be easier to stop. What if we have a bike moving at 300 kilometers per hour, fast and furious? And truck is heavier, of course, but it's moving at, let's say, 20 kilometers per hour. So now, which one would require a greater force to stop it? Now, that's a tricky question. We can't just guess it. We'll have to calculate it because we'll have to consider both the parameters here, mass and velocity. Hence, we have invented this term called momentum, which takes into consideration both the quantities of mass and velocity. Let's understand Newton's second law of motion. Now, Newton had observed that the rate of change of momentum of any object is directly proportional to the force applied on it and takes place in the direction of the force applied. That means that when you apply a force on an object, its momentum changes. Or in simple language, its velocity changes. If you're driving a car, it has a certain momentum, mass into velocity. If you press the accelerator, you're applying a force on it. Your car will accelerate, your velocity will increase, so your momentum will increase. And this increase in momentum depends on the increase in force applied by the engines. More the force, more is the increase in momentum. We can increase the velocity of a car from 0 to 30 kilometers per hour in 10 seconds or maybe in just 3 seconds. So how fast the momentum changes depends on how much force we are applying. If you apply a lot of force, the momentum will change very quickly. The velocity will change very quickly. Often we assume that the mass remains constant. So when I say momentum is increasing, we think that the velocity is increasing because the mass is assumed to be constant, which may not always be true. I'll come to that soon. Now let's derive a mathematical expression for Newton's second law. First of all, momentum is mass into velocity. So what is the meaning of change in momentum? Change in momentum means like P2 minus P1, which can also be written as delta P. Delta simply means a small change. We could have written this as P2 minus P1 as well, the final momentum minus initial momentum. That is equal to change in mass into velocity. So change in momentum, change in mass into velocity. Now, mass is constant, right? I mean, when you accelerate your car, the mass of the car doesn't increase, only the velocity increases. So mass is constant. So we can say that change in momentum is equal to the mass into change in velocity, which could also be written as mass into V minus U. V minus U is change in velocity, final velocity minus initial velocity. So we can write it in either form. However, when is this true? When two assumptions are made. Assumption number one, mass is constant. Now you may imagine that, but that is always true. Well, not quite. For example, when the rocket is launched, the fuel in it is burnt. The liquid hydrogen and oxygen is burnt. A lot of gases are given out. So its mass is decreasing. But in our day-to-day life, we can assume it to be constant. So we'll have to mention this, that the mass is constant. And the second assumption we are making is that the velocity is less, very less than the speed of light. Einstein's theory of relativity makes it very clear that when our velocity increases a lot, if it approaches even, let's say, 10% the speed of light. Speed of light is 3 into 10 raised to 8 meters per second. It is the fastest thing in the universe. Nothing can travel as fast as light, or not even close to it, for day-to-day objects. Our cars move at a minuscule fraction of the velocity of light. But we have observed in experiments that if some particles or any object moves at close to speed of light, the mass increases. The mass, which we always assume to be constant, it isn't. But what if you were in a rocket, a future rocket, advanced technology, taking you at 50% the speed of light? at such a huge velocity, your mass will increase significantly. Now, that cannot be ignored. So mass can also change. If that happens, then we cannot bring m out. In that case, we would say that only this statement is true. However, for our day-to-day experiences, we can use this formula also, given that we are assuming these two things. Rate means upon time, how fast the thing is changing. So rate of change in momentum would be the change in momentum upon time. Again, here we can assume mass to be constant. Rate of change of momentum is equal to mass, which is assumed to be constant, into the rate of change of velocity. If velocity is approaching the velocity of light, then this is the correct equation. This is an assumed equation. What is the meaning of rate of change of velocity? Acceleration. So we substitute that and we get the formula, the rate of change of momentum is equal to mass into acceleration. Now, the second law of Newton says that the rate of change of momentum is directly proportional to the force applied and takes place in the direction of the force applied. So we can replace delta P upon delta T as F. However, since there is a proportionality sign, we should introduce a constant of proportionality also in the equation. Unfortunately, we have assumed this constant to be 1 by definition, which makes the equation very simple. F is equal to ma. So this is the simple equation for Isaac Newton's second law of motion. Force is equal to mass into acceleration. But this is not universally true. If you remember here, I have made two assumptions. So if you want the true equation without any assumptions, according to Newton's second law, then it would be this one. Or you can replace this with F. So F is equal to delta mv upon delta t. What is the use of this Newton's second law? Now this is the general form of Newton's second law of motion. With the help of this, we can understand the units of force. For example, 1 Newton force is the force required to produce an acceleration of 1 meter per second square in a mass of 1 kg. So 1 Newton is equal to 1 kg into 1 meter per second square. This is the SI unit. What if we want to convert this into a CGS unit? The CGS unit for force is dyne. 1 dyne is the force required to produce an acceleration of 1 centimeter per second square in a mass of 1 gram. And the acceleration is in the direction of the force applied, of course. So let's find the relationship between 1 Newton and 1 dyne. 1 kg is 1000 gram. 1 meter will be 100 centimeter. That's 3 zeros, 2 zeros, 10 raised to 5 gram centimeter second squared is equal to 10 raised to 5 dyne. So 1 Newton is equal to 10 raised to 5 dyne. Now the applications of this Newton's second law. Question number 1. While catching a ball, the cricketer withdraws his hands along with the ball. Why does he do that? If you've seen the fielder, when he catches the ball, he moves the hand down and then he catches it. He doesn't just catch it like this. He moves the hand downwards. That means if the ball was moving with a velocity of, let's say, 50 meters per second, if you catch it without moving your hand downwards, you just catch it. That means that you are decreasing its velocity from 50 meters per second to 0 meters per second in a split second. There is a huge deceleration happening here. The rate of change of velocity, that is the rate of change of momentum, is great out here. So a lot of force is exerted by the ball on your hand. This may hurt your palms. On the other hand, if we catch it and move it downwards with the ball, we are decelerating it slowly. Let's say it took us 2 seconds to bring it to a complete stop. So from 50 meters per second, we started decreasing its velocity to 40, 30, 20, 10, 0. So because the time duration increased, the denominator increased, the force will decrease. It's inversely proportional. That's why it is easier for them to catch the ball like that. Let's take another example. Athletes often land on sand after taking a high jump or even a long jump. Why do they land on sand? Why not on concrete ground or the earth? The moment he lands on the concrete, his velocity becomes 0 suddenly. So again, the same logic here. The time duration for the change in velocity is so short, and smaller the time duration for the change in momentum, that is the change in velocity, the more will be the force exerted on the feet and he may be injured. On the other hand, if there is sand out here, then he doesn't come to a stop immediately. The feet press against the sand, it sinks a little bit in, it takes a couple of seconds for him to come to a stop completely. So there is a deceleration which is slightly slower. It takes more time for the momentum to change, to come to 0. And more the time, less is the force exerted. So there is no injury that way. When the glass vessels fall on a hard floor, they break. But they do not break when they fall on a carpet or sand. If a brittle glass vessel falls on the marble floor, it will break immediately. Same logic here. On the marble floor, the velocity becomes zero quickly. On the other hand, if it falls on a carpet, the carpet has some thickness. It's like a sponge. It absorbs some of the energy. The glass comes to a stop after a little longer duration. And longer the duration for the change in momentum, less is the force exerted and it won't break. Now let me tell you why the second law of motion is a fundamental law, because the first law can be derived from it. You see, in this equation, what if force is zero? No force is applied on an object. If the force is zero, then the mass, which cannot be zero, will remain as it is, but the acceleration will have to be zero. That means whenever no force is applied on some mass, it does not accelerate. That means its velocity doesn't change. So if it was at rest, it will continue to be at rest. If it is in a uniform motion, it will continue to be in its uniform motion. So that is the first law, derived from the second law equation.
Physics Chapter 3c, Linear Momentum and Newton's second law of motion. Linear momentum is a product of mass and velocity. So the formula is P is equal to m into v. It's a vector quantity, so it has a direction. Its SI unit is kilogram meter per second, and CGS unit is gram centimeter per second. Change in momentum is change in mass into velocity. Here the delta is called the change. So delta P can also be written as P2 minus P1, that is final momentum minus initial momentum. So the change in mass and velocity can either be because the mass has changed or the velocity has changed. If either of them changes in an object, the momentum will obviously change. But usually, when the object is traveling, we can assume the mass to be a constant. So another way of writing this is change in momentum is equal to the constant mass multiplied by the change in velocity. But in reality, mass is not constant at very high velocities. Yes, mass also changes. As you move faster, your mass increases. That's as per Einstein's theory of relativity, which we don't see in our day-to-day life because that effect is negligible. Our velocities are less than speed of light. That is, the velocities of our day-to-day objects are extremely small compared to the velocity of light, which is 3 into 10 raised to 8 meters per second. We don't even travel at 0.1% the speed of light. So we can imagine mass to be constant. However, it has been proven that when an object, like a subatomic particle, travels at close to the speed of light, then the mass is not constant, it changes. So then this equation cannot be used. Then we have to use the original equation, which is change in mass or velocity. So the two assumptions made for this equation are that the mass is constant and that the velocity is less than the speed of light. This formula is cancelled. Now that we've understood change in momentum, let's understand the rate of change of momentum. There are alternative methods to this. This method can be cancelled. We shall study this one. So whenever the word rate comes, it means upon time. So the rate of change in momentum is the rate of change in mass into velocity. But here we can remove m out because we have assumed it to be a constant, and we have assumed that velocity is much less than the speed of light. And change in velocity upon time is nothing but acceleration. So substituting that, we get the equation change in momentum upon time, that is the rate of change in momentum, is equal to mass into acceleration. But this is true only under the two assumptions made. One, mass is constant, which may not always be the case. For example, when the rocket is launched, as it is moving up, the mass of the rocket decreases because the fuel is being used up. And the second assumption is velocity is less than speed of light. Now let's talk about the Newton's second law of motion and the derivation of the formula of the second law of motion, F is equal to ma. Newton's first law had defined force qualitatively, but now Newton's second law gives us the quantitative value of force, that we have an actual formula to measure it. Second paragraph cancelled. This formula, F is equal to ma, means that force is directly proportional to mass and it is directly proportional to acceleration also. Means more the mass, more force is required to move it or bring it to a stop. Also, more the acceleration you want to produce, more is the force required. So graphically, it can be shown like this. Force and acceleration are directly proportional, so the graph is a straight line. Similarly, force and mass are directly proportional, so again the graph is a straight line. But if you consider these two terms, mass and acceleration, force being constant, then they are inversely proportional, like this. So the graph is a curve called hyperbola. Inversely proportional means if the mass increases, then the acceleration produced will decrease if the force is constant. For example, if you apply the same force on a bike and on a truck, in which case will a greater acceleration be produced? In a bike, because its mass is less. Now, since force is equal to mass into acceleration, now we can define some SI unit of force called Newton. 1 Newton is the force which, when acts on a body of mass 1 kg, produces an acceleration of 1 meter per second squared. And the CGS unit is dyne. So, can you think of the definition of dyne using this formula? 1 dyne is the force which, when acts on a body of mass 1 gram, produces an acceleration of 1 centimeter per second squared. Next, relationship between Newton and dyne. Now, we know that 1 Newton is 1 kg into 1 meter per second squared. Converting them into CGS units, we finally get 10 raised to 5, that is 100,000 gram centimeters square per second squared, which is 10 raised to 5 dyne. So, this derivation may come in exam. But what about this formula? How do we derive this one? Well, let's go back to our original proposition that the rate of change of momentum is mass into acceleration. And by the way, there are two assumptions here. Mass is constant and velocity is much less than the speed of light. Now, according to Newton's second law, the force applied is equal to the rate of change of momentum. And the rate of change of momentum, we have just proved, is mass into acceleration. Hence, we say that force is equal to mass into acceleration. So the statement of Newton's second law is the rate of change of momentum of a body is directly proportional to the force applied on it, and the change in momentum takes place in the direction in which the force is applied. So after all, force and momentum are vector quantities, so the direction matters. But here, instead of directly proportional, I have used equal to sign, simply because the constant of proportionality k is assumed to be 1. But remember, F is equal to ma is a special equation which holds true only for day-to-day objects under the two assumptions. In reality, the universal equation is F is equal to delta mv upon delta t. Here there are no assumptions. Only when the velocity is less than the speed of light and there is no change in mass can we assume that force is equal to ma. So remember these two assumptions. This may come in the exam. And Newton's second law is the fundamental law, because the first law can be derived from it. Let's see how. F is equal to ma. If force is 0, then acceleration will also be 0. That means that whenever there is no net force acting, there is no acceleration in the object. That is, the object will continue to be in its state of rest or of uniform motion in the absence of force. That is Newton's first law. Now let's study some examples of the second law in our day-to-day life. Cancel these couple of sentences. First, while catching a ball, the cricketer withdraws his hands along with the ball. Again, this is cancelled, and so is the sentence. Now we know that force is equal to rate of change of momentum. That means smaller the value of t, greater is this fraction, or greater is the force. Larger the time interval, less is the force. They are inversely proportional. So remember, more time it takes to change the momentum, less force is applied. So when a cricketer doesn't catch the ball directly but is withdrawing his hand, slowing down the ball and then coming to a stop, you are increasing the time of change of momentum. And whenever you increase the time of change of momentum, you are decreasing the force with which the ball hits your hand. Cancel these sentences. even cancel this formula and just mention when the time is very little, the force exerted by the ball on the hands of the cricketer is greater. But if he pulls back his hand, the time taken is much longer, then the force exerted by the ball is lesser. Again, cancel these equations. The second GR, athletes often land on sand after taking a high jump, because if you're landing on sand or foam, you are increasing the time taken for the change in momentum, so decreasing the force exerted on your feet, so you don't get injured. The same logic happens when a glass vessel falls on a carpet or on sand. On a hard floor, it comes to a stop immediately within a less time interval, so there is a higher rate of change of momentum, so greater force is applied. But on sand or on carpet, it comes to a stop after a slightly longer time interval, so the change in momentum is slower, so less force is applied. So mark this as a GR as well.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.